Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R Software. So you can recall that in this course up to now we have learned about different measures of central tendency and different measures of variations. So these are the two important characteristics which gives us a fair idea about the different hidden properties of the data structure. Now, from this lecture, we are going to start our new topic which is about movements. So, you know that data structure may have different properties, and now we are interested in studying the shape of the density curve or the shape of the density plot, or I would say how the data is concentrated, how it looks like, whether it is symmetric or unsymmetric, and what about the hump of the curve. That is what we want to know. In order to understand those properties, we need a concept about movements. Movements are certain statistical functions which explain us and help us in providing different type of information about the statistical structure of the data. So in this lecture, we will talk about different types of moments, raw moments, central moments, absolute moment. In the next lecture, we will see how we can compute them in the R software. And after that, we will study the concept of skewness and kurtosis, which are on the which are based on the concept of actually movements. So that is why we need this background. So let us begin this lecture and try to understand the concept of movements. So in this lecture, we are going to talk about the raw movements, central movements, and absolute movements. Right. So the first question come here: what is a movement? So movement is only a statistical function which is used to describe different types of characteristics and feature of the frequency distribution. For example, these movements can reflect on the central tendency of the data, dispersion or variability, symmetric nature, or peakedness of the frequency curve. Peakedness means hump, right? So it is something like this. Symmetry means whether the curve is like this one or this one or this one. That means the data is concentrated either equally on both sides of the central value, or it is skewed, right? And similarly, peakedness is about the hump of the curve, whether the hump of the curve is here or more than this or less than this, right? So these are the different statistical properties or the features of the density curve which help us in getting some more information about the data, right? And so now we are going to discuss about movements for two types of data. One is here ungrouped data, which is actually the discrete data, and it is obtained on a variable or random variable x, like I say here x1, x2, xn. And second type of data is the data on the continuous variable, or this is a group data. That means the data has been obtained. It has been tabulated in, say, k class intervals in the form of a frequency table, and the midpoints of those class intervals are obtained like this. So suppose if I say I have here k class intervals like E1 to E2, E2 to E3 up to Ek minus 1 to Ek, and then we obtain their midpoints x1, x2, xk, and then we obtain their absolute frequency f1, f2, fk. So f1 is the absolute frequency of class interval E1 to E2. Similarly, E2 to E3 class interval has absolute frequency f2, and so on, right? And capital N here is f1 plus f2 plus fk, that means the sum of all the frequencies. Now, first we try to define the movement about any arbitrary point. Suppose the point here is capital A, right? This can be anything, right? This can be any arbitrary value or mean, arithmetic mean, median, or anything else, right? So if I define the movement about arbitrary point A, then we have like here in general about A, about mean and other things. So in this case, the rth movement of a variable x about any arbitrary point based on the observations x1, x2, xn is defined for ungrouped data, that is discrete data, is here like this: 1 upon n summation I goes from 1 to n xi minus a raised to the power r. Right. So what we are trying to do, we are trying to find out the deviations of the individual data point around A. Then I am taking its rth hour, and then I am trying to find out its arithmetic mean. Right. It's like this, and this is denoted here as a mu r prime. Right. So that's the standard notation for this rth moment. And the same thing if I define in the case of continuous data or a group data, then it is defined exactly on the same concept as we have used earlier. I will try to take here xi minus a, these deviations. I will take its rth hour, and then I will try to find out its arithmetic mean. Summation I goes from 1 to k fi into xi minus a raised to the power of here r divided by here capital N, which is here the sum of all the absolute frequency. So yeah, so because this is the rth moment actually, so we also denote here as a mu r prime. So this is the rth moment about any arbitrary point capital A. Right. Now in this case, in case if you choose this arbitrary point A to be 0, right, then the rth movement around A equal to 0 is called as raw movement. And basically if you try to see here, we are trying to obtain these movements on the basis of given sample of data. So basically this is actually the rth sample movement. So for ungrouped data, that is the discrete data, the rth raw sample movement is defined here as say 1 upon here n summation I goes from 1 to n xi raised to the power of r. Right. So you can see here that in this definition, in case if you substitute here A is equal to 0, then you get here the rth raw movement, or the same thing will happen in the case of group data also. If you substitute here A equal to 0, then you get here the rth central movement. So similarly I can define here the rth sample based movement for the group data as here like this: mu r transpose is equal to 1 upon capital N summation I goes from 1 to k fi xi raised power of here r. So this is the same thing here actually. You are trying to find out actually the arithmetic mean of xi raised power of r values. Right. So you try to write down here summation fi xi raised power of here r divided by summation fi in the case of group data, and in the case of ungrouped data you are simply trying to find out the arithmetic mean of the values of xi raised to the power of here r. Right. So this is how we define the raw movements. Now if you try to see what is the significance of this raw movements. In case if you try to look at this structure, and if you substitute here r equal to say here 1 and 2, what do you get here? Or similarly in the case of group data also, if you substitute here r equal to 1 and r equal to 2, then what do you obtain here? Please try to observe, and this will give you an idea that why movements are needed and what we were doing up to now. So if you try to see here in the case of ungrouped data, if you put here r equal to 1, then you get here mu 1 prime is equal to 1 upon n I goes from 1 to n summation xi. What is this quantity? Can you identify? This is simply your arithmetic mean. And same is the case when you are trying to consider the group data. If you substitute here r equal to here 1, then you get here 1 upon capital N summation I goes from 1 to k fi xi, which is your here mu 1 prime. So this is also the definition of the arithmetic mean when you are trying to consider the or when you are considering the group data. Now, similarly, if you substitute here r equal to 2, then in the case of ungrouped data, you get here a quantity like arithmetic mean of the squared values of xi's, right, which is here 1 upon n, summation I goes from 1 to n xi square, and this is denoted here as say mu2 prime. And same thing happens in the case of group data here, that you get here mu2 prime is equal to 1 upon capital N, summation I goes from 1 to k fi xi square, right, where capital N is this summation fi, right. So, well, in the case of r equal to 1, you can very easily identify that the first raw movement is the arithmetic mean. And in the case of r equal to 2, you will see this, the second raw movement, this will help in giving us the value of the variance. Do you remember the variance was defined here as a 1 upon n summation I goes from 1 to n xi square minus x bar square, right. So, if you try to see, I can write down this variance here as say mu2 prime minus x bar is the arithmetic mean, so mu1 prime square, right. So, second raw movement will help us in getting the value about the variance, and the same thing is true for the this raw movement, second raw movement for the group data also. We had defined the variance, if you try to recall, as here 1 upon n summation fi xi square I goes from 1 to k minus x bar square. So, this will again become here mu2 prime minus mu1 prime square, right. So, this r equal to 1 will give us the idea about the arithmetic mean from this raw movements, and the second raw movement will help us in giving us the information about the variance. Now, what happens when r is equal to 0? So, when r is equal to here 0, then you can see here that mu 0 prime in both the cases is actually here 1. For ungrouped data as well as group data, this is equal to 1, right. Now, we discuss the idea about central moments. So, as you have seen that in this case, when you have used the a equal to 0, then you got the raw moments. Now, I am asking you, substitute a equal to here arithmetic mean here as well as here. Then you see what happened. When you try to use capital A equal to here sample arithmetic mean, then we get here the central moments, right. So, the movement of a variable x about the arithmetic mean x bar, they are called as central moments. So, if I have the sample of data x1, x2, xn, then the rth sample central moment for ungrouped data will be defined here as say 1 upon n summation I goes from 1 to n xi minus x bar raised to the power of here r. So, this is the same thing that I try to consider the deviation around the arithmetic mean. I take their rth hour and then I try to find out their arithmetic mean like this. So, this is how you can remember this definition without any problem. And same thing is true for the case of group data also, that we take the deviation from arithmetic mean xi minus x bar, we take their rth hour and then we try to find out their arithmetic mean. Say summation on the based on 1 upon capital N summation I goes from 1 to k fi xi minus x bar raised to the power of here r like this. So, these are your here rth central moment, right. And now you can see here what they are trying to give, as we have considered the case of r equal to 1 and r equal to 2, what happens to these central moments. So, when I try to substitute here say r equal to here 1 and 2, and the same thing is here r equal to 1 and 2. So, you see what will happen here. So, in the case of here when I substitute here r equal to 1, this is here 1 and this becomes here 1 upon n summation xi minus x bar, which if you try to solve will become here 1 upon n summation I goes from 1 to n xi minus 1 upon n into n times x bar. So, you will see here this quantity is nothing but your x bar. So, this will become here x bar minus x bar, which is equal to 0. That is what I am trying to write down here. So, the first central movement is always 0, right. So, first central movement is 0. Now, if you substitute r equal to 2 here, then you get here like this. So, you can see here what is this? This becomes here 1 upon n summation I goes from 1 to n x I minus x bar whole square, and this is your here mu 2. Now, can you identify what is this thing? This is nothing but your sample variance, right. If you try to recall, this is how you have defined the variance. So, this second central movement is variance. So, first raw movement is arithmetic mean, and first central movement is always 0, and second central movement is your variance. And the same thing happens in the case of group data also, that the value of here mu 1 is 1 upon n summation I goes from 1 to k f I x I minus x bar, and if you try to solve it, this becomes here 1 upon n I goes from 1 to k f I x I minus 1 upon n, say here x bar into summation I goes from 1 to k f I, right. So, summation f I is your nothing but your here n. So, this I can write down here, this is your here x bar minus x bar into n upon n. So, this becomes here 0. So, this I am trying to show you here. So, the first central movement in the case of group data is also 0. Now, if you try to put here r equal to 2, then mu 2 is defined here as say 1 upon capital N summation I goes from 1 to k f I x I minus x bar whole square. Now, if you try to identify, this is nothing but the definition of your variance based on the sample data, or this is sample variance. So, the second central movement is variance, right. So, now you can see first raw movement is arithmetic mean, first central movement is 0, and second central movement is variance. And in case if you try to substitute here r equal to 0, then in this case you get here mu 0 equal to here 1 upon n summation I goes from 1 to n, say here x I minus x bar is 0, which is equal to here 1 upon n summation I goes from 1 to k, say here 1. So, this is your here at total frequency n upon here n, which is equal to here 1, and the same story hold for the group data also. So, for r equal to 0, mu 0 is 1 for grouped as well as ungrouped data. So, this is what you have to keep in mind. And now, let me try to find out the relationship between the central and raw movements. One relationship I already had shown you here. If you try to see here, this is I shown you here, right. And if you try to see here, I can also show you here once again, that if you try to write down this here mu 2 can be written here as say 1 upon n summation x I square minus say x bar square. And if you try to recall this algebra, I had shown you earlier. So, this is your here mu 2 prime, and x bar your here is mu 1 prime square, right. So, this is the same thing which I am trying to show you here, that if you try to see about the r equal to 0, mu 0 and mu 0 prime both are equal to 1. The central movement r equal to 1 here, this is equal to 0. When you are trying to take here r equal to 2, then I already have shown you that mu 2 is equal to mu 2 prime minus mu 1 prime whole square. Similarly, in case if you try to write down for r equal to 3, like some 1 upon n summation I goes from 1 to n, say x I minus x bar cube, which is your here mu 3 for r equal to 3, then and if you try to expand it, then you will get here the relationship mu 3 is equal to mu 3 prime minus 3 times mu 1 prime into mu 2 prime plus twice of mu 1 prime cube. And similarly, if you try to write down here mu 4 for r equal to 4, you will get here 1 upon n summation I goes from 1 to n x I minus x bar is power of here 4. And if you try to expand it, and then if you try to substitute the values, you get here mu 4 is equal to mu 4 prime minus 4 mu 3 prime into mu 1 prime plus 6 times mu 2 prime into mu 1 prime square minus 3 times mu 1 prime raised to the power of 4. So, this is a relationship between the central and raw moments. So, if you know the values of raw moments, then you can compute here this central moments, right. Now, let me try to give you idea of one more concept here. This is about Shepard's correction for moments. What is this Shepard's correction? Actually, you see, when we are trying to consider the ungrouped data, then we have the values here x1, x2, xn. And when we are trying to, this is your here ungrouped data. And when you are trying to consider this ungrouped data as group data, then what do? You try to classify these observations into class intervals, right. Now, when you are trying to classify them into class intervals, so what do you assume? That all the, actually can you try to count the frequency, and you try to say that all the values are concentrated in the middle point of the interval. So, when we are considering the group data, we always assume that all the frequencies are concentrated at the middle part of the class interval. For example, in case if I take here some data here 10, 11, say here 12, 14, say 17, 18, 19. Now, if I create here two class intervals, say 10 to here 15 and here 16 to 20. Now, you will see here these 1, 2, 3, 4. So, the frequency in this interval f1 will be 4 and frequency in the class interval of 16 to 20 will be f2 will be 3. So, what you are trying to see actually here, if you try to plot this data, this will be like here 10 is here, 11 is here and so on. But when you try to create here the class interval, say here if I say here 10 to say here 15 and suppose here up to here 20. So, what we assume here, although these values are somewhere here, here, here or here, 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 so on, but we assume that all these values that f1 equal to 4 is concentrated in the middle part of this class interval. And similarly, the absolute frequency f2 equal to 3, that means there are 3 observations in the class interval between 15 to 20, they are concentrated at the midpoint, right. It is like actually this. So, now the reason is that if you look at the frequency value f1 equal to 4 or say f2 equal to 3, then my question is this, can you tell me the individual values? I mean, if I hide this 10, 11, 12, 14 and 17, 18, 19, then by looking at f1 equal to 4 and f2 equal to 3, can you tell me what are those values which are in the interval 10 to 15 or what are the values which are in the interval of 16 to 20? No. So, that is why because of this assumption that all the values are concentrated in the middle part of the class interval, some error is introduced, right. Because usually all the values will not actually be concentrated at the center, they will be scattered over the interval. So, this error is called as grouping error. So, this grouping error is introduced. Now, this Shepard correction is meant for taking care of this grouping error, right. So, Shepard suggested that such an effect can be corrected in calculating the moments by using the information on width of the class interval, right? And Professor Shepard, or Professor W.F. Shepard, he proved that if the frequency distribution is continuous and the frequency taper off to 0 in both the direction, the grouping effect can be corrected as follows. And he has given here some expression, right? But before that, let us assume the width of the class interval is C, right? So we are assuming that all the intervals are of the width C only. So now Shepard has suggested that there is no correction required in the first raw movement. So first we consider the raw movement, and then in the second raw movement, the correction is required here as say that the second raw movement value is to be adjusted by the value c square upon 12. So this second corrected raw movement will become mu 2 prime minus c square by 12, means the second raw movement minus c square by 12. And similarly, the third corrected raw movement becomes mu 3 prime minus c square by 4 mu 1 prime. And similarly, the fourth corrected raw movement becomes mu 4 prime minus c square by 2 mu 2 prime plus 7 by 240 c raised to the power of 4, right. And similarly, if you try to consider here the central movements, then the second corrected central movement becomes mu 2 minus c square by 12. The third central movement does not require any correction, so it will remain as the same. So mu 3 corrected and mu 3 will be the same. Fourth corrected central movement will be like mu 4 minus c square by 2 mu 2 plus 7 by 240 c raised to the power of here 4. Why there is no mu 1 corrected? Because this value was always actually 0, right. So this is how we can correct our raw and central movements with this grouping error. Now after this, I give you here one more idea, which is about absolute moments, right. So you can recall that when we had discussed the idea about constructing the different measures of variation based on the concept of deviation, then we had constructed the absolute mean, deviation and variance, right. So if you try to see, in one case we had taken the absolute value of deviation, and in other case we had considered the squared value of the deviation. So based on those concepts, now we can make it here more general, and we can define here the absolute moments, right. So now in case you have the ungrouped data, say x1, x2, xn, then the rth sample based absolute moment is defined here like this, that you consider here the deviation xi minus x bar. Yeah, the deviations are considered around the arithmetic mean. Well, that can be any point actually, but I am considering here arithmetic mean, because this is how these absolute moments are defined. Then you try to consider its absolute value, and then you take its rth hour, and then find out its arithmetic mean, 1 upon n summation I goes from 1 to. So this is called here as say rth absolute moment, and this is denoted as absolute value of mu and r. So this is 1 upon n summation I goes from 1 to n absolute value of xi minus x bar raised to the power of here r. And similarly for the group data, if you try to do the same exercise, that if you consider the deviation xi minus x bar and consider its absolute value, take its rth hour and try to find out its arithmetic mean, 1 upon capital N I goes from 1 to k fi into xi minus x bar raised to the power of here r, right. So this here capital N is equal to the sum of all the frequencies, and x bar is computed as in the case of group data, right. So this rth absolute moment is denoted as absolute value of mu and this r, then 1 upon n summation I goes from 1 to k fi xi minus x bar absolute value and its power r. So this is how we define the absolute moments, right. And if you try to, for example, take here r equal to 2 here, then you get here the same thing, right? That is, you here the variance, because absolute value of xi minus x bar with r equal to 2 is the same as, say, xi minus x bar whole square, right? So these are the some simple concepts about the moments. Well, these are simple some mathematical functions which have to be computed on the basis of data, but they have an advantage that they are giving us some information about the hidden tendencies or hidden properties about this data. So, you can see here that we have taken here, say, 4 moments: first moment, second moment, third moment and fourth moment. Similarly, you can take the fifth, sixth, seventh moment, and you can find out the relationship between central moment and raw moments, etc. But usually you will see that in the books we are considering only the 4 moments. The reason being, the first raw moment, this is giving us the information about mean of the data. The second central moment is giving us the information about the variability in the data. And similarly, you will see in the forthcoming lectures that the third moment is used to define the coefficient of skewness, which is measuring the symmetric property of the data, whether the data is symmetric or not around certain values. And similarly, the fourth movement is helping us in finding out the structure of data with respect to the hump of the curve, that is kurtosis, right. But what the fifth, sixth and higher moments are giving us the information is not known to us. So, up to now we do not know, although this mu5, mu6, etc., they all can be defined, they can be computed, but what the properties of the structure of the data they are trying to give us, that is unknown to us. So, that is why usually we are interested in the first 4 movements of the data. So, now my request is that please try to look into this definition, please try to understand them that how we are defining these functions and why these functions have been defined in such a way, right. And then, for example, I have given you the relationship between the central and raw moments for first 2 moments. Similarly, you try to see whether you are getting the same relationship for the third and fourth moment, which I have just given you this just statement. So, you try to look into this concept, practice them, and I will see you in the next lecture where we will see how we can compute these moments in the R software. So, you try to look at them, and I will see you once again in the next lecture. Till then, goodbye.